What would happen if you gave the same amount of heat to equal masses of water and gold? It turns out that the temperature of gold would rise almost 33 times higher than that of water. In this video, let's see where the heat energy goes and what temperature actually means. First of all, temperature measures the average kinetic energy per particle inside a body. When a body receives heat, the energy scatters among all the particles of the body, turning into their kinetic energy. So, to heat water and gold to the same temperature, we have to give each of their molecules the same amount of kinetic energy. But an atom of gold weighs 11 times as much as a water molecule. This means that in equal masses, water has 11 times as many particles to heat up. But even if there were an equal number of particles, the water temperature would still be at least 3 times lower. This is because a single atom of gold can only move around its 3 axes in space, but a complex water molecule has many more degrees of freedom. Molecules can also rotate and vibrate, stretch and bend, but these processes usually don't affect the kinetic energy of the particle. So it appears that the received energy becomes hidden inside the molecule itself, and the temperature rises much less than it should. At the same time, different molecules can interact with each other and hide energy in their interactions. For example, in liquid water, molecules can get so close to each other that atoms of different molecules can stick together and form multiple bonds. When such molecules receive energy, they spend much of it just breaking these bonds, leaving them with less kinetic energy. And that's why liquid water can absorb twice as much energy as water vapor or ice. This process is similar to the melting of solids, where a melting solid can absorb a lot of thermal energy without increasing its temperature by a single degree. This is because all particles in solids form bonds with each other, but these bonds are so strong that the particles cannot move freely and form a rigid crystal structure. However, they can vibrate in place, and as the temperature increases, they become more intense. At the melting point, their vibrations become so powerful that with a little more energy, a particle can break free from its bonds and become a liquid particle. And since this energy is only used to break the bonds without directly affecting the particles, it does not increase the temperature of the entire material. By the way, kinetic energy depends not only on speed or vibrations, but also on the mass of the particle. For example, the peculiarity of metals is that each of their atoms has several free electrons that can move freely within the metal. Since electrons have an incredibly small mass, they can move at incredibly high speeds even with a small amount of kinetic energy. This allows them to constantly collide with atoms and transfer their energy throughout the material almost instantly. That's why metals conduct heat faster than all other materials and can feel extremely hot to the touch compared to other surfaces of the same temperature. On the other hand, insulators such as wood or rubber consist of long and weakly linked chains of molecules. Inside such a chain, molecules have many interactions and connections that absorb a lot of energy. However, 2 different chains cannot interact directly and exchange heat. For example, wood easily conducts heat up through its fibers made of molecular chains, but barely conducts it across them. So, temperature doesn't tell you how much thermal energy is inside an object, it only tells you how much energy its particles can transfer upon collision with others. Complex molecules such as water can hide energy in multiple ways and avoid releasing it directly, which is why water can absorb much more heat than simple gold.